Alright, so this is the incline here, and I'm just going to pull this one here up. These are 2 kilograms. I'm going to put it up here, and that's just by lifting it. Of course, I could just lift it up here instead of using the incline, but there are things that are much heavier than that, and you really do want to use a simple machine such as the incline plane. And of course, this is just a demonstration, so I'm just going to lift these 2 kilograms up here, which is approximately 20 newtons, 19.6 newtons exactly. And now I'm going to pull them up the incline, and I expect, of course, to measure less force. The incline I measured to be 2 meters long, which means I should have an ideal mechanical advantage of about 2 meters versus the 1 meter I have over there. Actually, it's 90 centimeters, so a little bit over 2, which means I should be measuring only 10 newtons. But if you want to come close and just put the camera on here, and as I pull it up, you can see that I'm actually measuring 60 newtons. So it's not around 10 newtons, but 60 newtons. But of course, that's the friction in the board, which means I still have a mechanical advantage, and I may want to use the incline depending on how I'm using it. Of course, it's a very steep incline too, but it turns out that I actually have to use more work altogether, but I still have the mechanical advantage of having to apply less force. And that was actually it. So.
This is the analysis of the example data that I took for the inclined plane. And first I'm going to grab the equations for that analysis. Students don't need it here for the example data. I need it right now, but I don't want to have it in several places and then have to edit every single place all the time. That's why I only posted it in one place. I know it might be a little bit off the recording, so I'm going to try this one here. Maybe. Here we go. Whoops. There we go. Okay, so for the inclined plane, what I took was 2.00 kilograms was the load, and I wanted to lift it a height of 0.90 meters, and the slant length of the incline was 2.0 meters. So from that, I'm going to calculate the weight of the load is 19.6 newtons, because 2 kilograms times the acceleration of 9.8 is 19.6 newtons. Then the amount of work that I would use in order to just lift it, those 0.90 meters, is 19.6 newtons times 0.90 meters, and that comes out to 17.6 joules. I have my calculator lying on the side here, and I trust that you're going to plug in these numbers correctly. Let's just multiply these two numbers according to this equation here. Then the ideal mechanical advantage is the slant length over, so the 2.0 meters divided by the height of 0.90 meters. So it's a little bit over 2, comes out to 2.2 rounded. No units on this one here because you divide meters by meters. So that means that the expected effort force should be this much smaller compared to the load, which means that I would have to apply only roughly half of that force, and the equation is over here. Effort force equals load force divided by the ideal mechanical advantage, so 19.6 newtons divided by 2.2 comes out to 18.9 newtons. And of course, that is the idea of a simple machine. It reduces the amount of force necessary by quite a bit, in this case to about half. That would be the ideal one. However, you notice that I did measure 60 newtons because I have friction on the board. So I still have a mechanical advantage It's not that much as it should be, but still there's some in there. Of course, for a regular incline, you may not want to use as steep of an incline as what I did, because you want to reduce the amount of force appreciably and have a large mechanical advantage, actual and ideal. Okay, the work that is done with the incline is this one over here. So work with the incline is the force with which I actually moved it times the length. So 60 newtons times 2.0 meters comes, of course, out to 32 joules. And now the actual mechanical advantage is the load force. I'm sorry, the force of the load divided by the actual measured force, so 19.6 divided by 16 comes out to 1.2. So the actual mechanical advantage is only 1.2, 20%. The efficiency is the lifting force, the lifting work divided by the incline work, so 17.6 divided by 32 comes out to 55%. Ideally, we would get for an efficiency 100%, meaning that no matter how you do it, you exert the same amount of work. That means no matter how you do it, by lifting or by work with the incline, you come up with the same amount of work. You don't get a free lunch, but of course the work with the incline takes into consideration that there was friction on the board, and therefore this number here in this case is appreciably larger than this number, and that's why we only get an efficiency of 55%. You might get for your inclines efficiencies between 20 and 30%, because I recommend that you use more shallow inclines, but then for the more shallow inclines, you're going to have a larger mechanical advantage, which is the idea behind an inclined plane. So this was the analysis for my example data for the inclined plane.